currently in a climate crisis globally. We have rampant anthropogenic emissions that are impacting the climate on a large scale, and we need to deal with those emissions globally. One way that we're particularly interested in is called carbon mineralization. Essentially, we're taking atmospheric CO2 and we're trying to precipitate that as a mineral and lock that CO2 away in a mineral phase. A lot of people are probably familiar with the minerals that we're trying to go after, like calcite. You often get that in your teapots when you boil water. It's that little bit of grime that hangs around on the inside of your pot. We're trying to make those phases to help reduce emissions.
A lot of the sources for calcium and magnesium in the earth also come with a lot of iron. And people hadn't really answered the question of how we could use that iron, or whether we could use that iron effectively to also trap carbon dioxide. So what the synchrotron did was it let us see exactly where the iron was, identify what materials it was in, and we could then make predictions about how much there were and how efficient the reactions were. So the synchrotron was absolutely essential for the work. Now we have a better capacity to predict how much CO2 we can store using standard materials.
Critical minerals mining is going to be important for developing sustainable technologies. We're interested in minimizing the impacts of mining and how mining emissions can be reduced.